Welcome to this particular lecture. If you remember in the last lecture what we discussed is how to make the neural probes, right. So, these are the devices, these are single shank, these are multi shanks that are used to acquire the signal from the brain, that is why I say neural probes, right, or neural devices, or to apply electrical stimulation to certain region in the brain, right. So, either it can acquire the signals from the brain or it can provide or stimulate a certain region in the brain, right. So, we saw a little bit about what are those techniques. Let us understand little bit in detail, since we will have the lab class where we will show it to you how these systems or equipment or tool can be used. Okay. So, if you remember, we talked about physical vapor deposition. In physical vapor deposition there are three techniques. The first one is your thermal evaporation, the second one is electron beam evaporation, and the third one is sputtering, isn't it. And for the chemical vapor deposition there are several techniques, because it has CVD, within CVD which is chemical vapor deposition. Within that we have PCVD, LPCVD, APCVD, we have ALD, we have MOCVD, right, and so on and so forth. Then once you deposit this material, right, whether it is metal. Now in case of most of the devices that we will be learning as a part of this course, we will be depositing metal and insulator. Okay. There is no semiconductor in between, that is why we will stick it to either depositing metal or coating or depositing insulator. That two things we need to remember. So, for depositing metal or insulator we can either use CVD or PVD. PVD is physical vapor deposition, CVD is chemical vapor deposition. Once you deposit the metal, then you need to perform the lithography, so that you can pattern the metal so as to form the electrodes along with the contact pads, isn't it. So, these electrodes are recording electrodes or stimulating electrodes. So, for example, if this is the area, then either if I put an electrode, it can record the signals because it is a ECOG signal, right, this is the area of the brain, okay, or it can stimulate certain region in the brain. So, for that you need to have a metal, right. We will see electronics as a part of the TA class, right, how we design the electronics module to stimulate certain region in the brain, and we will also look into how to design this electronics, whether it is 8 channel or 16 channel, wired or wireless, using an intent chip. Okay. So, it is going to be very interesting because you will not only learn the way to design the device, but also how to acquire the signal and how to stimulate, right. So, how to design the electronics for the same. Now, we talked about photolithography because that is photons that are used to do the lithography. Lithography, as I yesterday or in the last lecture, right, when I recorded, have discussed that lithos and graphics, which comes from the Greek word, and there are certain steps in lithography which will be a separate class. And finally, we either etch it, which is anisotropic etching, or it is isotropic etching. We use wet etching or dry etching. In wet etching there are certain ways to etch certain metals. If you are etching the silicon as a substrate, then we call it as a micro machining. So, we will understand all this stuff in the following classes. So, now let us see the slide. If you remember, we discussed about this particular slide. Now, let us see the next slide. So, we start with the physical vapor deposition, and as it is written that PVD is more versatile method than chemical vapor deposition. Why? Because it allows to deposit almost all the materials used in fabrication. Okay. When you say almost all the materials, what does that mean? So, using PVD you can deposit metals, you can deposit semiconductor, you can deposit insulator. So, all three all three categories, right, materials falling in that we can deposit using PVD. We can also do the co-deposition, right, multiple materials deposition. So, in the case of PVD, the surface reaction occurs very rapidly, and so very little rearrangements of atom occurs on film surface. So, I will show it to you by drawing it in the next slide that what exactly this statement means. Okay. but you need to understand that the reaction occurs very rapidly. So, it is very rapid one, and then very little time, right, for what, for rearrangement of atoms on the film substrate. So, because of that, or as a result, thickness uniformity, shadowing by surface topography and step coverage can be very important issues. So, now let us understand in this module three things. One is your thermal evaporation, the second one is your e-beam evaporation, and the third one is sputtering. Okay. So, we will start with the thermal evaporation. So, when we use these two statements, right, that a reaction occurs, surface occurs rapidly and a little time for rearrangement of atoms, right, this is true for all the three systems or techniques, evaporation or e-beam or sputtering. Okay. So, here you can see there is a thermal evaporator, there is a e-beam evaporator, and which one is thermal and which one is e-beam? This one here is a thermal evaporator. Okay. This one here is a e-beam evaporator, this one here is also e-beam evaporator. Okay. So, these are all called physical deposition techniques. So, the methods or physical methods, right, produce the atoms that deposit on the substrate either by evaporation or by sputtering. Within evaporation you have thermal evaporation and you have electron beam evaporation, right. So, within evaporation there I have two and then there is a sputtering. So, this process physical vapor deposition is sometimes also called vacuum deposition. Why? Because the process is usually done in a evacuated chamber. Now, there is a reason of evacuating the chamber which we will discuss. However, you can see here the systems carefully, just see for a second and then we will continue. Okay. So, you have seen, right, now what you observed, what you observed. So, one thing that you may have observed in this system is, see, this is one kind of some system is attached here also and here also, right. Here you cannot see in this slide. What are these things, right, that I am putting an arrow here, this arrow or this one. These are your secondary pumps. Okay. These are your secondary pumps. So, the physical deposition techniques, you have primary pump and you have secondary pump. The primary pump is used to create a vacuum of 10 to the power minus 2 to 10 to the power minus 3 torrs. Okay. This is the vacuum that is created by the primary pump. Secondary pumps are different kind of secondary pumps are there, right. There is a Getter ion pump, there is a turbomolecular pump, right, and these secondary pumps are capable of getting us vacuum anywhere from 10 to the power minus 5 to 10 to the power minus 7 to 10 to the power minus 8 in certain cases torr. Okay. But without creating a base pressure of 10 to the power minus 2 to minus 3, we should not turn on the secondary pump. Very important statement, without you having the base pressure of minus 2 or minus 3 in the we should not start the secondary pump. Very important statement, you need to make sure that you follow this protocol. Okay. Now, having says that, let us understand a bit more. Let me just erase this one. So, one thing that we have seen is a secondary pump. Both arrows shows the arrows which are left here, this shows the secondary pump that is attached to the vacuum chamber. All right. Now, this particular system, right. So, let me just rub this one and get the pen back. Okay. So, this system is kind of manually operated. Okay. this one is automatic, this one is semi automatic. Okay. So, either it can be manual, it can be automatic, or it can be semi automatic. This is manual, this is automatic, this is semi automatic. Okay. Thermal evaporation and e-beam evaporation. Next what you see is windows. You see windows here 1 2 1 2 1 2, correct. Every system has 2 windows, right. What is the reason of having these windows? So, let us see what is the reason first. Okay. So, the reason of having these windows is to observe the metal that is melted or the material that is melted and the material that gets deposited onto a substrate. Now, where the substrate is kept. So, let me just give you some examples, show you something, and then we can go back to the previous slide. So, there is a chamber, right, that you have seen, there is a chamber, correct, and let us close the chamber. Now, here in the top you have a substrate holder. What is it called? Substrate holder. In the bottom you have a source holder. Okay. Substrate holder and source holder. Source. So, whatever material you want to deposit, right, is a source. So, this in this case, this one that we have used is also called boat, BOAT, boat. Instead of that, you can also use spiral kind of structure like this, right. So, this is also used as a source holder. Now, let us take a case of we want to deposit aluminum, right. So, these are aluminum chunks, but if I want to put a chunk in this source holder which is spiral in nature, it is difficult. How it will hold? It cannot hold, right. So, this is your aluminum, right, aluminum beads or chunks, whatever you want to say. So, in this case we will use wires, aluminum wires, and you can load it like this. So, this one would be aluminum wires. Easy, is very easy. Now, substrate. What are substrate? Substrate is any material on which we are going to perform the experiments or we have performed the deposition and lithography and whatever. So, the base material is our substrate. It can be silicon, it can be glass, it can be polymer, alright. It can be any other semiconductor other than silicon. Okay. So, polymer you can say plastics, right. So, these are polymers. So, you can use several different material as a base material that we call it as a substrate. Now, this substrate holder can hold many silicon wafers. Let us say we have 2 silicon wafers with a clip attached, so it will not fall. It is a clip that is attached, so that silicon wafer will not fall. Now, you do understand that this is exactly on the. So, when there is a deposition, the deposition will be like this, correct. Now, when you want to deposit this material and it evaporates, right. So, first what you need to do, this aluminum metal is in what? It is in solid structure, right. So, we need to first melt it and then it starts evaporating. So, when you melt it, right, how can you melt aluminum or any other metal or any other material? By heating, right. So, you can melt aluminum by heating. Since you are melting by heating, you are applying a thermal energy, right. So, you are applying thermal, and that is why it is called thermal evaporation. You are applying heat to melt the aluminum material and it gets melted and starts evaporating and depositing on the substrate. Substrate can be silicon, can be semiconductor, can be glass, can be polymer, any material, base material on which we want to deposit the metal or semiconductor or insulator. Easy. Now, you to create a vacuum, right, and we also discuss about the windows. We also discuss about the windows. So, we will come to that windows point. Okay. Since we are talking about this one, first thing you need to understand is there is something called this, you can see this checks, right, this box is called QCM. QCM. QCM stands for quartz, right, quartz, you know, quartz is what, crystal, quartz crystal, M for monitor. So, quartz crystal is used to monitor the rate of deposition of the metal onto the substrate which is loaded onto a substrate holder. So, this quartz crystal monitor works on what kind of effect principle? It works on piezoelectric. What is piezoelectric? When you apply a pressure, there is change in the voltage, right? Apply pressure, change in voltage, piezoelectric. Now, if there is a deposition of this metal onto the QCM, from the QCM we can read what is the rate of deposition of aluminum, right, because it works on the piezoelectric effect, and that rate of deposition of the metal or material can be converted into a readable form onto a display, and we will know what is the rate of deposition. Generally it is in angstrom per seconds, okay, is in angstrom per seconds. So, it is 10 angstrom or 50 angstrom or 100 angstrom, depending on how fast you want to evaporate this material, all right. Now, there is a shield, okay, it is a metal shield is here and it is a metal. So, this material cannot pass this metal sheet, you can say it is a shield, right, shield. So, this one is your shield, okay. Now, if the shield is between the source holder and between substrate holder, then the material that gets evaporated cannot reach substrate, easy, because it is a metal sheet, right, you cannot pass through metal. So, once you melt the aluminum, right, if you can observe. Now, to observe this melting of aluminum, what you require? You require a window, isn't it? When you, because once it is melted, then you open the shield so that the deposition starts, right. So, still it is melting, you do not open the shield, because it is not that complete melting, we have to wait so that the evaporation will start. If when it starts melting, it starts evaporating, but we do not want to do that. We want to melt all the aluminum pellets or chucks or bead, right, onto the loaded onto the boat, right, before we open this shield so that the evaporation will start. Now, how to observe this melting is by using the bottom window. You can see here, in this case here, in this case here. Easy, understood the role of window? The windows are to observe the melting is done or not. Now, that is okay. Now, we understood what is the role of the bottom window. What is the role of the top window? What is the role of top window? Now, you can understand this substrate holder, you want to see that the wafers are properly loaded, they are not falling, the deposition is occurring, right. Then you can use, and sometimes the substrate holders in all the new PVD rotates. What is the role of rotation? When you rotate the substrate holder and you deposit the material, the deposition is uniform. So, to rotate the substrate holder, right, such that the uniform deposition occurs on the way, onto the substrate. So, if you want to observe what is going on to the substrate or what is happening to the substrate, you can use the second window which is on the top here, 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 right. So, window 1 is for your source holder, window 2 is to look at the substrate loaded onto the substrate holder. Easy, right, easy, very good. So, QCM we talked about, so rate of deposition, shield we have to, so we have to rotate the shield, we have to rotate the shield. So, it will come out from the path, right, between the source and the substrate, it will come out of the path which is between source and substrate. Now, we say that all these PVDs are also called vacuum deposition, right, vacuum deposition. Why vacuum deposition? Why vacuum deposition? Because VAC UUM, okay, VAC UUM, vacuum deposition. Why vacuum deposition? Because we create a vacuum, but why to create a vacuum, right? Can we not deposit the material in the presence of air at atmospheric pressure? Why to create vacuum? That was the reason behind creating vacuum, right. So, the reason behind creating vacuum is to improve mean free path. What is mean free path? So, mean free path is a time that the material that is there that evaporates, right. So, atoms collides with another atom or molecule, right, in the chamber, right. So, how much path is it has travelled, right, from source to the substrate. If this is x, right, has it travelled full x or x minus some path, right, or x minus 2x, whatever it is, right, or it cannot be 2x, you know that. So, I am just saying example 10 centimeter is there, is it travel 2 centimeter or 5 centimeter or 8 centimeter, or there is no molecule that will hit or atoms that is hitting the another atom, right, and it has a large mean free path. So, mean free path is important because then the deflection would be less and the deposition would be faster and uniform. So, reason of having vacuum is to improve the mean free path, mean MEAN, mean, free FREE, free, path PATH, path. So, please Google it, so you know better about the mean free path. Okay. Now, if we see the slide, what we see next one is that there is a meter here, right, and there is a variac. What is that? Variac, VARIAC, variac. Variac is variable AC. So, we can vary the voltage. Here in E-beam evaporation, right, there is something else. So, first let us understand the thermal evaporation. Okay. So, we concentrate on this particular figure or picture, and here you have a current meter. You see here there is a current meter, because when you apply a voltage and this is a board, right, you apply a voltage across the board, right. So, you apply a voltage across the board. This board is nothing but a metal which has some resistance, right. So, when you apply voltage and there is a resistor, what will generate? Current will be there, right, current will generate, and because of the flow of current and I square R heating, which is also called Joule's heating, this resistor or the board, right, will start heating up. So, when it starts heating up, the material within it will start melting, correct. So, to apply this voltage, we use this variable AC variac, and you can observe the current in the current meter here. So, that is the reason of having the this particular block. Here if you see, it is a very faint image, I am sorry about that, but there is a LED display. Okay. In the new system there are LCD displays, you can see LCD here, right, or even you can see it here, right. So, in particular here this is the one. So, here you can see very clearly the rate of deposition, okay, and we can measure this rate in terms of angstrom per second, angstrom per second. So, whether LEDs or LCDs does not matter, this is just kind of display, but my point is in the system this is the LED one while the other two are LCD one. Okay. So, this display is used for what? What I said, that it is used for measuring the rate of deposition of the material that we are depositing onto the substrate. Another thing that you need to understand is that generally PVD is used for depositing metal, but it can be very well used for dielectrics as well. Generally it is for the metal deposition, but it can very well be used for dielectrics. Okay. So, we talked about vacuum, we talked about the primary pump, secondary pump, we talked about QCM, we talked about substrate, source, the power that is given to the source, it melts, it deposits, as simple as that, right. Now, what are the gauges to measure this pressure? Because we said 10 to the power minus 3, 10 to the power minus 6. So, where are these gauges, right? So, there are two gauges, one is called Pirani gauge and second is called Penning gauge. You see here, this is a gauge. Okay, this is a gauge. One is Pirani gauge for primary or for the vacuum which is in 10 to the power minus 2 minus 3 range, where while the Penning gauge is used for vacuum more than 10 to the power minus 3 torr or 10 like 10 to the power minus 4 and so on, okay, not really more, but in terms of range 10 to the power minus 4 onwards, right. So, Pirani is 10 to the power minus 2 minus 3, Penning is 10 to the power minus 4 onwards or minus 3 onwards in a way. So, the another thing here that I wanted to show it to you would be whether the substrate can be rotated or not. So, see, this is the rotation, this is the rotation, means of course, there is a motor that will rotate and so the substrate holder will rotate, right. So, this is the system that is on the top of the chamber which is connected to the substrate holder which is inside the chamber and will rotate the substrate. The reason of rotation is to have a uniform deposition of the material onto the substrate. Easy? All right. So, more or less I think I have discussed about the chamber, its vacuum pump, the gauges, the windows, LCD or LED displays, the variac, right, heating and other things. So, as you can now it just tell me one thing here, suppose I have aluminum, right, which is okay. I have a boat and I load the beads and I give a voltage and there is a current flowing, right, because this is a resistor. So, now what will happen is that this boat will heat up and the material starts evaporating, that much we have understood. If it is not aluminum, so that means that the melting point of source, in this case it is aluminum, right, should be way less than the melting point of source holder material. So, this boat is our source holder, isn't it? Boat is our source holder. The melting point of the source, so in this case it is aluminum, but if I do not want to use aluminum and if I want to use some other material, so which has a very high melting point. Suppose the melting point of the source, the statement here is that if we want to use thermal evaporation, then the condition is that the melting point of the source should be way less than the melting point of the source holder material, right. So, that this material which is boat will not melt, right, while the source is melting, in this case source is aluminum. But what if the melting point of source is greater than melting point of source holder? In this case what will happen? In this case we cannot use the thermal evaporation system. When the melting point of the source is greater than the melting point of source holder, we cannot use thermal evaporation system. Everybody understood this much? Easy to understand, right. So, this is a limitation. Then if I cannot use thermal evaporation, what should I do, right, what should I do? So, the question remains, how can we overcome this limitation? So, if the here there are 4 statements. The first one is that in evaporation techniques of physical vapor deposition, a vacuum chamber is pumped down to less than 10 to the power minus 5. We have seen that evaporation atoms from the source condense on the surface of the wafer, we have seen that as well, and then the heater can be of resistive type, generate tungsten filament, and it heats up as current flows through it. We also have discussed this thing. Next one is but the most popular is E-beam evaporation system, in which a high energy electron beam is focused onto a source in crucible using magnetic field. Now, the question is then why we have studied the thermal evaporation system? See, there are 3 systems, right, thermal evaporation, E-beam evaporation and sputtering. But the most popular in comparison of thermal or E-beam evaporation, that is the evaporation techniques, E-beam is better, and how E-beam works we will discuss in the next class. But the point is, depending on the method of evaporation hardware, evaporation techniques can be categorized as thermal evaporation and E-beam evaporation. So, like I said, either you heat it, which is thermally heat the material and melt it and deposit it, or you use electron beam and electron beam will fall and it will heat the material and material deposits. Now, we will see the advantage of E-beam evaporation in the next class, and little bit understood about the thermal evaporation. Let us see the thermal evaporation first, and then we will end this class, so that next class we focus on the E-beam evaporation. Okay. So, if you see the slide, only one slide for you, you can see here that there is a vacuum, correct, in this figure, then there is a source material, there is a heater, right, here there is a heater or resistance, and there is a wafer holder at the top, right, there are wafers attached to it. Wafers is nothing but your substrates, right. And when you create when you apply a voltage, right, this to the source material or source holder, the material within the source holder will melt and it will evaporate. This is the shield that I was talking about, right, in the previous things, and this one is one of the source holder. It can have 4 sources, for source 1, source 2, source 3 and source 4. 4 sources are there. Okay. So, this is within the chamber we have taken the photos. There are 4 sources. So, you can have 4 different deposition, whichever source you heat up, right, the source holder you heat up, the source within that source holder would start evaporating. So, thermal evaporation relies on thermal energy supplied to the crucible or to boat to evaporate atoms. Evaporate atoms travel through the evacuated space between source and the sample and stick to the sample. Surface reaction usually occurs very rapidly, and there is little time of rearrangement of surface atoms after sticking. Now, you can understand, right, as soon as you melt the material, it will immediately start depositing. So, it is so fast that the atoms cannot rearrange itself, right. That is the statement that we have seen in previous slides. And second is thickness, uniformity and shadowing by surface topography and step coverages are issue. So, because to improve the thickness or uniformity of the deposition, we rotate the substrate holder. Still there is a shadowing effect which is not possible to overcome, and there is some kind of step coverage issue. What is step coverage? So, suppose this is a substrate holder, okay, this is a substrate holder, and you have a substrate loaded onto it, and on substrate you have some material like this. Okay. So, this is your material, this is your silicon and this is your substrate holder. All right. Now, let us say this is your silicon dioxide for example. Now, you want to deposit metal everywhere. So, you have a boat and then you have some material and you evaporate it. So, it start evaporating like this, correct, everywhere. What happens is, if I zoom this area, only this area, okay, so it is like a step, no, this is like step. This region, which one, the material will not get deposited properly on the step area, alright, and that is why the step coverage in the thermal evaporation or e-beam evaporation is an issue, which is not that much when we talk about sputtering, and even better than sputtering for the step coverage will be your chemical vapor deposition. So, with that, let us not stretch it further, and we will stop it here, and let us focus on the next topic, which is your e-beam evaporation as a part of next class. So, till then you take care, see, understand, ask, right. You are free to ask us questions to the forum, and as I promised, we will answer your questions as early as we can. Till then, you take care.